Hello, friend. Welcome back to another quiet journey through the cosmos. If you're here settling in as the day fades, know that you're exactly where you need to be. Tonight, we're not chasing sleep with silence. We're chasing it with fire, the kind that burns 93 million miles away, yet still finds ways to touch us. Some mornings, the sun rises gently like a whisper of gold across the horizon. It warms your skin. It wakes the birds. It feels safe. But other mornings we rarely talk about, the sun doesn't rise. It screams. It tears itself apart in ways we can't see with our naked eyes, sending storms of plasma and radiation hurtling through space. And sometimes, just sometimes, those storms find Earth. Tonight we're going to watch the sun, not for its warmth, but for its violence. Not for what it gives, but for what it could take away. Before we begin, if you find comfort in these quiet journeys through science and shadow, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Now, let's drift. The sun sits there every single day looking the same, a constant, a friend. We plan our lives around it, wake with it, sleep without it, trust it to return each dawn. But constancy is an illusion. The sun is not calm. It never has been. Beneath that golden surface, beneath the light that makes life possible, there's chaos. Plasma hotter than anything on Earth, twisting and turning at millions of degrees. Magnetic fields tangling like fishing line, left too long in the current. And every so often, something snaps. When it does, the sun doesn't just glow, it erupts. It flings pieces of itself into the void, great waves of charged particles moving at millions of miles per hour. Scientists call these solar storms, coronal mass ejections, solar flares. But the name doesn't capture the scale. Imagine if 1 billion nuclear bombs detonated at once and you'd still be nowhere close to the energy released. These aren't explosions in the way we understand them. They're more like the sun tearing open its own skin. And here's the strange part. Most of the time, we don't even notice. The Earth spins quietly through space, protected by invisible shields we'll talk about later. The storms pass by, or they hit us so gently that all we see are beautiful lights dancing in the Arctic sky. But not always. Sometimes the storms are stronger. Sometimes they don't just graze us, they strike full force. And when they do, the world we've built, the technology we depend on, becomes fragile as paper. You might be wondering, has this happened before? The answer is yes, and not that long ago. September 1st, 1859, a Thursday morning in England. Richard Carrington, an amateur astronomer with a private observatory, was doing what he did most mornings, sketching sunspots through his telescope. Sunspots were a curiosity back then, dark blemishes on the sun's face that came and went without much explanation. Carrington had been tracking them for years, mapping their movement, trying to understand their rhythm. That morning, he was watching a particularly large group of spots when something impossible happened. 2 intensely bright patches of white light appeared within the dark spots. They blazed so brilliantly that he could see them, even through the sun's blinding glare. Carrington stared, unsure if his eyes were playing tricks. He ran to fetch a witness. By the time he returned less than a minute later, the lights were already fading. He didn't know it yet, but he had just witnessed the most powerful solar flare ever recorded in human history. 17 hours later, the sky caught fire, not with flames, but with light. Auroras, the northern lights, descended from the poles and swept across the entire planet. People in Cuba saw them. People in Hawaii saw them. Miners in the Rocky Mountains woke in the middle of the night, convinced it was dawn, and started making breakfast. In New England, you could read a newspaper by the glow of the aurora alone. The colors were so vivid, so strange, that some thought the world was ending. Others thought it was a sign from God. But the most terrifying effects weren't in the sky. They were in the wires. Telegraph systems, the cutting-edge technology of the era, went haywire. Operators reported sparks leaping from their equipment. Some received electric shocks. In a few cases, the telegraph paper caught fire, even though the machines had been disconnected from their batteries. The storm had induced so much electrical current in the wires that they no longer needed external power. The sun itself had become the battery. Carrington didn't understand what he'd seen. Neither did anyone else. The science of solar storms didn't exist yet. But what happened that day, what we now call the Carrington event, was the Earth's most violent encounter with the sun in recorded history. It was a warning written in fire and magnetism that the star we depend on is not as gentle as it seems. And here's the part that should make you pause. If the Carrington event happened today, it wouldn't just create pretty lights. It could take down the global power grid, disable satellites, erase the internet, send us back quite literally into the dark. Think about that for a second. The same sun that gives us life, that warms the oceans, that grows the food, that makes every single breath possible, also has the power to shatter the civilization we've built. We live every single day in the orbit of a star that loves us and threatens us in equal measure. And we've mostly forgotten that it can hurt us. So, tonight as you settle in, as your breathing slows and the world outside fades, we're going to explore what happens when the sun loses its temper. We'll walk through the science, the plasma, the magnetic fields, the invisible forces that govern our star. We'll look at the storms themselves, what they are, how they form, how they travel across the emptiness of space to find us. We'll revisit 1859, and we'll ask the question no one wants to answer. What would happen if it occurred again right now, in our hyper-connected, electricity-dependent world? But we'll also talk about beauty. Because these storms, as dangerous as they are, create some of the most breathtaking phenomena in nature. The auroras, the shimmering veils of green and red that dance across polar skies. They're born from violence, but they look like magic. And maybe that's the point. Maybe the universe is trying to remind us that destruction and creation are often the same thing, just seen from different angles. You don't need to understand everything. You don't need to memorize the science or fear the sky. Just rest. Let your mind wander and listen. Let curiosity do the work, because the sun, ours and the one we see every single day, is stranger, more powerful, and more dangerous than most of us ever imagine. And it's worth knowing why. So, take a breath, settle in. The story is just beginning, and the sun is already awake. Let's see what happens when the sky catches fire. But before we watch the storms themselves, we need to understand where they come from. We need to look beneath the light into the hidden violence that churns inside the star. Because the sun, for all its brightness, is not what it seems. The sun looks smooth from here, a perfect circle of light glowing steadily in the sky, unchanging, except for the slow arc it traces from dawn to dusk. We see it every day, and every day it looks the same. But that smoothness is a lie. The surface we see is not a surface at all. It's a roiling ocean of plasma, a sea of ionized gas so hot that atoms fall apart. And beneath that glowing shell hidden from our eyes, there's violence beyond anything we can imagine. If you could peel back the light layer by layer, you'd find a furnace. At the sun's core, 27 million degrees Fahrenheit. Hydrogen atoms collide with such force that they fuse into helium, releasing energy in the process. That energy doesn't rush straight to the surface. It takes thousands of years to claw its way outward, absorbed and re-emitted, countless times bouncing through the dense layers like a pinball trapped in a machine. By the time it reaches the surface and escapes into space as light, that photon has been traveling for millennia. The sunlight warming your face right now was born in the core when the pyramids were still new. But energy isn't the only thing moving inside the sun. There's also plasma, not solid, not liquid, not gas, but something else entirely. Plasma is matter stripped down to its rawest form, electrons torn free from atoms, charged particles flowing like blood through the sun's interior. And where there are charged particles, there are magnetic fields. Those fields twist and tangle as the plasma moves, coiling like invisible ropes beneath the surface. Scientists suggest that this motion, this constant churning, creates what's called a dynamo effect. the same principle that powers the magnets in your refrigerator, but scaled up to cosmic proportions. Here's where it gets strange. The sun doesn't rotate as a solid object. The equator spins faster than the poles, completing a full rotation in about 25 days, while the polar regions take nearly 35 days. This uneven spin drags the magnetic field lines, with it winding them tighter and tighter, like twisting a rubber band over and over. Eventually, those field lines become so stressed, so tangled, that they punch through the surface. When they do, they create what we call sunspots. Sunspots are cooler than the surrounding plasma, about 6,500 degrees Fahrenheit, compared to the surface's 10,000 degrees. That might not sound cool, but it's enough to make them appear dark against the brighter background. They're not small either. A single sunspot can be larger than Earth. Some are large enough to swallow Jupiter. Galileo saw them in 1610 through one of the first telescopes ever built, and he was astonished. The sun, which Catholic doctrine held to be perfect and unblemished, had marks on its face. It was wounded. It was real. But sunspots aren't just dark patches. They're symptoms of something deeper. Think of them as scars where the sun's magnetic field has broken through the surface like cracks in the skin of a balloon stretched too tight. And where there are sunspots, there are active regions, places where the magnetic energy builds and builds until it has nowhere left to go. That's when the sun doesn't just glow, it explodes. Research shows that the magnetic field lines near sunspots are often twisted into complex loops arching high above the surface before diving back down. Plasma flows along these loops, trapped by the magnetic forces like beads sliding along a wire. But sometimes the tension becomes too much. The loops snap. When that happens, the energy stored in the magnetic field is released all at once, a process called magnetic reconnection. It's like cutting a taut guitar string. The string doesn't just go slack, it whips violently, releasing all its stored energy in an instant. In the sun's case, that energy doesn't dissipate quietly. It erupts as radiation, as light, as waves of charged particles flung into space. It becomes a solar flare. Scientists have been studying this process for decades, trying to understand exactly how reconnection works and why some active regions produce massive eruptions while others remain quiet. The answer, it seems, lies in geometry. When magnetic field lines with opposite polarities come close to each other, they can cancel out and rearrange, releasing energy. It's elegant in theory, but brutal in practice. A single reconnection event can release as much energy as 1 billion atomic bombs. And it's not random. The sun follows a cycle, rising and falling in activity, roughly every 11 years. At solar minimum, the surface is calm, with few sunspots and little activity. At solar maximum, the sun is covered in spots swarming with magnetic chaos. The most recent maximum occurred in 2014, and we're climbing toward the next one now. Some cycles are stronger than others. Solar Cycle 19, which peaked in 1958, was one of the most intense on record. Solar Cycle 24, which just ended, was one of the weakest. No one knows for certain why the cycles vary, but the consequences are always the same. More sunspots mean more eruptions, and more eruptions mean more storms heading toward Earth. But here's the part most people don't realize. The sun doesn't need to be at maximum to produce dangerous storms. Even during quieter periods, a single large active region can unleash chaos. It only takes one twisted loop, one moment of magnetic instability to send a wave of plasma hurtling toward us. The sun's violence isn't predictable in the way we'd like. We can track the cycles map, the sunspots monitor the magnetic fields, but we can't always see the eruption coming. Beneath the light, beneath the warmth, the sun is a battlefield. Magnetic forces clash and twist, plasma boils and churns, and every so often something gives way. It's not malicious. The sun isn't angry. It's just doing what stars do, burning, churning, existing at the edge of chaos. But we live in its shadow, and we've built a world that depends on stability. A world of satellites and power grids and delicate electronics. a world that wasn't designed to withstand the fury of a star. So, when you look up and see the sun shining peacefully, remember you're not seeing the whole picture. You're seeing the afterglow, the surface, the light that escaped. Beneath that glow, hidden in layers of plasma and magnetism, there's a storm waiting to happen. And when it does, when the magnetic field snaps and the energy breaks free, it doesn't stay on the sun. It rushes outward, riding the solar wind, traveling at millions of miles per hour. Some of those storms fade into the darkness. Others find planets. And just some find us. The question isn't whether the sun will erupt again. It will. The question is, when the next storm comes, will we be ready? But before we can answer that, we need to understand what these eruptions actually are. We need to see the fire up close, not the gentle warmth of sunlight, but the sudden, violent rage of a solar flare. There's a moment just before the flare when everything goes quiet. The magnetic field lines stretch tighter, the plasma slows, the sun holds its breath. And then, without warning, it lets go. In less than a second, the energy of 10 million hydrogen bombs floods outward as light as X-rays, as radiation moving at the speed of light itself. By the time we see it happening, it's already hit us. There's no time to prepare, no time to react. The flare has already won. Solar flares are the fastest violence the sun can produce. Unlike the slower storms we'll talk about later, flares don't hurl matter into space. They hurl energy, pure electromagnetic radiation, blazing across 93 million miles in just 8 minutes. When they reach Earth, they don't knock on the door. They flood in invisible and immediate, bathing the daylight side of the planet in a wave of high-energy particles. Most of the time, our atmosphere absorbs the worst of it, but not always. And when the flare is strong enough, the consequences ripple through our technology like cracks in glass. Scientists classify solar flares by their X-ray brightness using a scale that sounds deceptively simple: C-class, M-class, and X-class. C-class flares are small, barely noticeable, the kind that happen multiple times a day during active periods. M-class flares are medium strong enough to cause brief radio blackouts in the polar regions, strong enough to make scientists pay attention. But X-class flares, those are the monsters. They're 10 times more powerful than M-class, and the scale doesn't stop at X1. It keeps climbing. X2, X5, X10. The Carrington flare. The one Richard Carrington saw in 1859 is estimated to have been an X45 or higher. Some researchers believe it might have topped X50. That's off the scale we use today, beyond anything we've measured with modern instruments. To put that in perspective, an X1 flare releases the energy equivalent of 1 billion megatons of TNT. That's roughly 66,000 times the energy of the atomic bomb dropped on Hiroshima. An X10 flare, 10 billion megatons. The numbers stop making sense at that point. They become abstractions too large to feel. But here's a way to ground it. If you converted the energy from a single X-class flare into electricity, it could power the entire United States for 100,000 years. And the sun produces these flares regularly, sometimes multiple times a month during solar maximum. The mechanism behind a flare is magnetic reconnection, the same process we touched on earlier. But it's worth understanding in more detail because reconnection is one of the most elegant and brutal phenomena in plasma physics. Imagine two magnetic field lines with opposite polarities, one pointing north, one pointing south, brought close together by the churning motion of the sun's plasma. Normally, field lines don't cross. They repel, slide past each other, avoid contact. But if the conditions are right, if the plasma moves just so the lines can touch, when they do, they annihilate. The magnetic energy stored in the field converts instantly into kinetic energy, heat, and radiation. The plasma accelerates to a significant fraction of the speed of light. Particles that were drifting lazily a moment before are suddenly moving fast enough to punch through steel. This happens in a region above the sun's surface called the corona, a halo of superheated plasma that extends millions of miles into space. The corona is strange. It's hotter than the surface below, it reaching temperatures of several million degrees, even though the surface itself is only 10,000 degrees. Scientists still don't fully understand why, though they believe magnetic reconnection plays a role. The corona is where flares are born, where the magnetic field is most twisted and unstable, and it's where we've been watching with increasing precision as our instruments have improved. The first flare ever recorded was purely accidental. Carrington wasn't looking for flares. He didn't even know they existed. He was sketching sunspots when he happened to glance up at the exact moment the sun exploded. For over a century after that, flares were studied indirectly through their effects on Earth radio. Blackouts, auroras, disruptions, and telegraph lines. But in the 1970s, satellites changed everything. For the first time, we could watch the sun continuously without the interference of Earth's atmosphere. We saw flares in X-rays and ultraviolet light in wavelengths invisible to the human eye, and we realized just how often the sun erupts. During solar maximum, there can be multiple X-class flares per week. During solar minimum, months might pass without one, but they're always coming. The sun never stays quiet for long. One of the most famous flares in recent history occurred on November 4th, 2003, part of a series of eruptions known as the Halloween storms. An X-28 flare exploded from a massive sunspot region, saturating the sensors on the GOES satellites that monitor the sun. The instruments maxed out. Scientists later revised the estimate upward to X-45, making it one of the strongest flares ever recorded. But here's the twist. The flare wasn't aimed at Earth. It erupted from a region near the sun's limb, angled away from us. If it had been facing us directly, the effects could have been catastrophic. We got lucky. The universe doesn't always aim its guns at us, but sometimes it does. And when it does, we feel it. Flares don't just release light. They accelerate particles, protons, electrons, ions to near relativistic speeds, creating what's called a solar energetic particle event, or SEP. These particles race ahead of the slower-moving plasma storms reaching Earth in minutes to hours. When they arrive, they can penetrate satellites, damage solar panels, degrade electronics, and pose a radiation hazard to astronauts in space. During the January 2005 flare and X-7 event, airlines were forced to reroute flights over the polar regions to avoid exposing passengers and crew to elevated radiation levels. The particles don't reach the ground. Our atmosphere is thick enough to stop them, but at cruising altitude there's less protection. Pilots and frequent flyers receive more radiation exposure than most people realize. And during a major SEP event, that exposure can spike dangerously. There's a common misconception that solar flares are fireballs, literal flames shooting off the sun. They're not. There's no combustion, no oxygen, no fire in the way we understand it. A flare is a magnetic explosion, a release of energy that manifests as light and radiation. If you could watch one up close, not that you'd survive, you wouldn't see flames. You'd see a sudden brightening, a flash of X-rays and ultraviolet light, maybe a shock wave rippling through the plasma. It would be beautiful and lethal in equal measure, but it wouldn't look like fire. It would look like the sun tearing itself apart just for a moment before stitching itself back together. And here's the unsettling part. We still can't predict them with precision. We can identify active regions on the sun, places where the magnetic field is tangled and unstable, and we can say, this region has a high chance of producing a flare in the next 24 hours. But we can't tell you exactly when it will happen or how strong it will be. It's like watching a pot of water about to boil over. You know it's coming, but you don't know the exact second. And in the case of solar flares, that uncertainty matters. Because when an X-class flare erupts facing Earth 8 minutes later, the radiation arrives and there's nothing we can do to stop it. Flares are fast, violent, and beautiful. They're proof that the sun, for all its apparent constancy, is a star in flux, a body governed by forces we're still learning to understand. They remind us that light isn't always gentle, that energy can be a weapon as easily as a gift, and they're only part of the story. Because while flares travel at the speed of light, hitting us almost instantly, there's something else the sun can hurl at us, something slower, heavier, and far more dangerous. Not light, not radiation, matter itself. Imagine the sun tearing off a piece of itself and throwing it into space. Not light, not radiation. Actual matter, billions of tons of plasma ripped from the corona and flung outward at millions of miles per hour. It sounds impossible, like something from a nightmare, but it happens regularly. And when one of these plasma clouds finds Earth, it doesn't just pass through us. It slams into the invisible shield that protects our planet, and for a few hours or days, that shield struggles to hold. These eruptions are called coronal mass ejections, or CMEs, and they're the sun's heaviest punch. While a solar flare is a burst of energy, a CME is an explosion of substance, a bullet of magnetized plasma, weighing as much as Mount Everest launched into the void at speeds that can exceed 5 million miles per hour. Think about that. 5 million miles per hour. That's fast enough to cross the distance between Earth and the Moon in less than an hour. Fast enough that when a CME is heading toward us, we have maybe a day, sometimes less, to prepare. And most of the time we don't see it coming until it's already too late to do much about it. CMEs begin the same way flares do, with magnetic reconnection in the sun's corona. But instead of just releasing energy, the reconnection tears open the magnetic structure, holding the corona in place. It's like puncturing a balloon. The plasma that was trapped in magnetic loops suddenly finds itself free, and it rushes outward, carrying the magnetic field with it. The sun essentially spits out a chunk of its own atmosphere. If you could watch it in real time, you'd see a bright arc lifting off the sun's surface, expanding as it moves like a shock wave rippling through water. Except, this wave isn't water. It's a billion-ton cloud of ionized gas traveling through the vacuum of space, and it carries with it enough magnetic energy to disrupt an entire planet. Not all CMEs are created equal. Some are slow and weak, drifting outward at a leisurely pace, dissipating before they reach anything of consequence. Others are monsters. The fastest CME ever recorded occurred on August 4th, 1972, clocking in at nearly 9 million miles per hour. It reached Earth in just 14, and 6 hours a record that still stands. Most CMEs take 2 to 3 days to make the journey, giving us some warning. But that 1972 event, if it had been aimed more directly at Earth, if it had carried a stronger magnetic payload, it could have been catastrophic. As it was, it caused disruptions in power grids and knocked out a few satellites. We got off easy, but the speed was a warning. The sun can move faster than we thought. Here's the key difference between a flare and a CME. A flare is like a gunshot, fast, immediate, over in minutes. A CME is like a cannonball, slower but infinitely more devastating when it hits. Flares can damage satellites and disrupt communications. Yes, but CMEs can knock out entire power grids. They can erase data from hard drives. They can induce currents in pipelines strong enough to accelerate corrosion in railways, strong enough to throw signals offline. When a CME hits Earth, it doesn't just touch the technology in space, it reaches all the way down to the ground. The mechanism is something called geomagnetically induced currents, or GICs. When the CME's magnetic field collides with Earth's magnetosphere, the invisible bubble of magnetism that surrounds our planet, it compresses and distorts it. That distortion causes rapid changes in Earth's magnetic field. And those changes induce electrical currents in anything conductive on the ground. Power lines, pipelines, railway tracks, even the Earth's crust itself. These currents aren't subtle. During strong geomagnetic storms, GICs can exceed 100 amperes in a single transformer. Transformers aren't designed for that. They overheat, they fail, and when they fail, the power goes out. Not for minutes, but for weeks, sometimes months. depending on how quickly replacement transformers can be manufactured and installed. On March 13th of 1989, ACME struck Earth and caused a geomagnetic storm, strong enough to black out the entire province of Quebec, Canada. 6 million people lost power in less than 2 minutes. It happened at 2:44 in the morning. The grid operators barely had time to react. The CME compressed Earth's magnetosphere, induced massive currents in the power lines, and fried several transformers. Hospitals switched to backup generators. Traffic lights went dark. The blackout lasted 9 hours, but it could have been worse. Engineers managed to bring the system back online relatively quickly. If the storm had been stronger, if more transformers had failed, Quebec could have been in the dark for weeks. And this wasn't even a particularly powerful CME. It was strong, yes, but nowhere near the scale of the Carrington event. Which raises the question, what happens when the really big one hits? Scientists estimate that a Carrington-level CME striking Earth today could cause up to $2 trillion in damage in the first year alone, with a recovery period stretching 4 to 10 years. That's not hyperbole. That's the assessment from the National Academy of Sciences. $2 trillion. The collapse of power grids across entire continents. Satellites rendered inoperable. GPS Shao. Communication networks severed. Modern civilization, for all its resilience, is built on a foundation of electricity and electronics, and both are vulnerable to the same thing, rapid changes in magnetic fields. A strong enough CME doesn't have to destroy the equipment directly. It just has to change the magnetic environment fast enough, and the equipment destroys itself. But here's where it gets even more unsettling. CMEs don't arrive alone. Often they're accompanied by flares, by solar energetic particles, by shock waves that ripple through the solar wind ahead of the main plasma cloud. These shock waves can reach Earth hours before the CME itself, triggering preliminary disturbances, confusing forecasters, making it harder to predict the full impact. And sometimes the Sun launches multiple CMEs in quick succession, each one compounding the effects of the last. During the Halloween storms of 2003, the Sun produced at least 7 X-class flares and several major CMEs over the course of 2 weeks. It was one of the most intense periods of solar activity in modern history, and it reminded everyone paying attention that the Sun doesn't erupt politely one storm at a time. It erupts in waves. There's also the issue of direction. Most CMEs don't hit Earth. The Sun is a sphere, and CMEs erupt in all directions. We occupy a tiny slice of the sky, as seen from the Sun, less than 0.5% of the total solid angle. Most storms miss us completely, sailing off into the emptiness of space or striking other planets. Venus gets hit. Mars gets hit. Mercury, closest to the Sun, gets pummeled constantly. But Earth. We're in the line of fire only occasionally, and yet occasionally is enough. Because when a CME is aimed directly at us, what scientists call a halo CME, because it appears to surround the Sun in images taken from Earth's perspective, there's no dodging it. It's coming, and we have to ride it out. One of the most infamous near misses occurred on July the 23rd, 2012. A massive CME erupted from the Sun, one of the fastest and most powerful ever recorded. It tore through space at nearly 7 million miles per hour, ripping past the orbit of Earth. But we weren't there. Earth had already moved past that point in our orbit. The CME missed us by about 9 days, the time it took for Earth to travel far enough along its path that we were no longer in the line of fire. If it had erupted a week earlier, it would have hit us directly. Researchers later analyzed the data and concluded that the magnetic structure of that CME was similar to the Carrington event. If it had struck Earth, it could have caused widespread long-term blackouts, damaged satellites, disrupted global supply chains, and set back technological infrastructure by years. We didn't get hit because the universe's timing was slightly off. That's how close it was. 9 days. A cosmic blink. So when people ask, How dangerous are solar storms, really? The answer is it depends on where Earth is when the sun decides to erupt. We can't control the sun. We can't steer CMEs away or weaken them. All we can do is watch, measure, and hope that when the big one comes, we're not standing in its path. But hope is not a strategy, and luck runs out. The sun will erupt again, and sooner or later, another Carrington-level CME will be aimed directly at us. The question is, what happens when it hits? To answer that, we need to understand the shield that's been protecting us all along the invisible magnetic bubble that stands between us and the full fury of the sun. Earth has been here for 4.5 billion years, orbiting the same violent star, bathed in the same solar wind, struck by the same storms. And yet, life exists. Oceans remain liquid. The atmosphere hasn't been stripped away into space. We're still here, fragile and breathing on a planet that should by all rights look like Mars, cold, dry, and lifeless. So, what's the difference? What stands between us and the full force of the sun's rage? The answer is invisible, ancient, and absolutely essential. It's a magnetic field generated deep in Earth's core, extending tens of thousands of miles into space. It's a shield we can't see, can't touch, but without it, none of us would exist. The magnetosphere, as scientists call it, is Earth's first and only defense against solar storms. It's not a solid barrier. It's more like a bubble of magnetic force constantly shaped and reshaped by the solar wind, the stream of charged particles flowing outward from the sun at all times, not just during storms. On the side of Earth facing the sun, the magnetosphere is compressed, squeezed inward by the pressure of the solar wind, until it's only about 6 to 10 times the radius of Earth itself. On the night side, it stretches out into a long tail, called the magnetotail, extending more than 1 million miles into space like a comet's tail made of magnetism instead of dust. This tail is part of the reason Earth's magnetic environment is so complex. The field doesn't just sit there symmetrically. It bends, it stretches, it responds to every push and pull from the sun. When a coronal mass ejection hits the magnetosphere, it does something extraordinary. It absorbs the impact. The plasma slams into the outer edge of the field, a boundary called the magnetopause, and the magnetosphere compresses even further, sometimes shrinking to just 4 Earth radii on the day side. Research shows that during the most intense geomagnetic storms, the magnetopause can be pushed so close to Earth that satellites in low orbit find themselves temporarily outside the protected zone, exposed to the full brunt of the solar wind. But the field doesn't break. It bends, it flexes, and most importantly, it redirects. The charged particles in the CME can't pass straight through. They're forced to flow around the magnetosphere like water around a stone in a stream guided along the field lines toward the poles. This is where the magic happens. The particles that do manage to penetrate the magnetosphere funnel down the field lines toward the polar regions, collide with atoms in the upper atmosphere, primarily oxygen and nitrogen. When a high-energy proton or electron strikes an oxygen atom, it excites the electrons in that atom, bumping them to a higher energy state. When the electrons drop back down, they release the excess energy as light. Oxygen emits green and red. Nitrogen emits blue and purple. The result is the aurora borealis in the north, the aurora australis in the south, curtains of colored light dancing across the polar skies. It's one of the most beautiful phenomena in nature, and it's born from violence. The auroras are literally the atmosphere bleeding light ionized by particles that traveled 93 million miles just to crash into it. But the magnetosphere doesn't protect us perfectly. It can't. During a strong geomagnetic storm, the influx of particles overwhelms the system. The magnetosphere becomes saturated, and currents start flowing through the ionosphere, the layer of atmosphere between 50 and 600 miles up, where auroras occur. These currents generate secondary magnetic fields, which in turn induce currents in the ground, in power lines, in anything conductive. It's a cascading effect. The storm doesn't have to physically reach the surface to affect us. It just has to disturb the magnetic environment enough that the disturbance propagates downward, and the stronger the storm, the deeper that disturbance goes. There's a region within the magnetosphere called the Van Allen radiation belts discovered in 1958 by physicist James Van Allen using data from the Explorer 1 satellite. These belts are zones of intense radiation, trapped particles spiraling back and forth along Earth's magnetic field lines, held in place like flies caught in a web. There are two main belts: an inner belt that sits about 1,000 to 6,000 kilometers above Earth's surface, and an outer belt that extends from about 13,000 to 60,000 kilometers. The inner belt is relatively stable, populated mostly by high-energy protons. The outer belt is more dynamic, swelling and shrinking in response to solar activity filled primarily with electrons. During a geomagnetic storm, the outer belt can surge with additional particles, and sometimes a temporary third belt forms, lasting days or weeks before dissipating. These belts are a hazard. Satellites passing through them are bombarded by radiation, which can damage electronics, degrade solar panels, and even cause total failures. The Hubble Space Telescope, orbiting at about 550 kilometers safely below the inner belt, still experiences minor glitches from radiation exposure during solar storms. Higher satellites, especially those in geosynchronous orbit at 35,786 kilometers, sit right in the outer belt and are particularly vulnerable. Engineers design satellites with radiation, shielding redundant systems and software that can reboot after a glitch. But there's only so much protection you can add before the satellite becomes too heavy and expensive to launch. It's a constant trade-off: protection versus performance. And then there's the ionosphere itself, the layer where auroras glow and where radio waves bounce. The ionosphere is sensitive to solar activity. During the day, sunlight ionizes the upper atmosphere, creating layers of charged particles that reflect certain radio frequencies back to Earth, enabling long-distance communication. At night, without sunlight, the ionization fades and the reflection weakens. But during a solar storm, the ionosphere becomes supercharged. Flares flood it with X-rays, causing what's called a sudden ionospheric disturbance, or SID. Radio signals at certain frequencies are absorbed instead of reflected, causing blackouts that can last minutes to hours. High-frequency radio used by aircraft and ships for long-distance communication simply stops working. Pilots lose contact with air traffic control. Emergency responders can't communicate. GPS signals, which travel through the ionosphere on their way to the ground, become distorted and unreliable. Your phone might tell you you're standing in the middle of the ocean when you're actually in your driveway. Now imagine Earth without its magnetic field. Imagine the solar wind hitting the atmosphere directly unimpeded. That's Mars. Mars once had a magnetic field generated the same way Earth's is by a dynamo in its molten core. But about 4 billion years ago, Mars's core cooled and solidified. The dynamo shut down. The magnetic field collapsed. And without that shield, the solar wind began stripping away the Martian atmosphere molecule by molecule over millions of years. Today, Mars has less than 1% of Earth's atmospheric pressure. It's cold, dry, and bombarded by radiation. Any water that once flowed on its surface either froze underground or was lost to space. Mars is a warning. It shows us what happens when a planet loses its magnetic protection. It dies slowly under the relentless assault of its own star. Earth's core is still molten, still churning, still generating the magnetic field that has protected life for billions of years. But that field isn't static. It shifts. It weakens in some places and strengthens in others. The magnetic poles wander, drifting slowly across the surface. Right now, the North Magnetic Pole is moving from Canada towards Siberia at a rate of about 55 kilometers per year, faster than it's moved in centuries. And every few 100,000 years, the field does something even stranger: it flips. The North and South magnetic poles reverse. compasses that once pointed north would point south. These reversals are recorded in ancient rocks in the magnetic alignment of iron particles frozen in lava flows. The last reversal happened about 780,000 years ago. We're overdue for another, statistically speaking. And when it happens, and it will happen eventually, the process takes thousands of years, during which the magnetic field weakens significantly, possibly by as much as 90%. What would that mean for solar storms? Honestly, no one knows for certain. The field would still exist, but it would be weaker, less organized, possibly full of gaps. Auroras might appear at the equator. Radiation exposure at the surface could increase. Satellites would be more vulnerable. It's unsettling to think about, but there's no evidence that past reversals caused mass extinctions. Life survived, but past civilizations didn't have satellites. They didn't have power grids. They didn't depend on GPS or global communication networks. We do. And a weaker magnetic field during a major solar storm could mean the difference between a manageable disruption and a civilization-altering catastrophe. But for now, the shield holds. Day after day, year after year, the magnetosphere deflects. The solar wind absorbs the CMEs, funnels the particles toward the poles, where they paint the sky in colors we still don't fully understand. It's been doing this since life first crawled out of the oceans, since the first cells divided, since Earth cooled enough to form a crust. The shield is older than all of us, older than all recorded history, and we owe everything to it. But it's not invincible. It can be overwhelmed, and when the storm is strong enough, even Earth's ancient defense begins to crack. Which brings us back to 1859, to the day the shield was tested like never before, and the world caught a glimpse of what the sun is truly capable of. September 1st, 1859. The sky was clear over Red Hill, England, and Richard Carrington was alone in his observatory doing what he'd done nearly every clear day for the past 8 years, watching the sun. He had no idea that in the next 60 seconds, he would become the first human being to witness something that science didn't yet have a name for. He didn't know that what he was about to see would change our understanding of the sun forever. And he certainly didn't know that 17 hours later, the entire world would feel the consequences. Carrington wasn't a professional astronomer. He was a brewer's son who'd inherited enough money to pursue his passion for the stars. He'd built a private observatory on his estate, equipped it with a modest refracting telescope, and dedicated himself to one particular obsession: sunspots. Every morning, weather permitting, he would project an image of the sun onto a white screen and carefully sketch the dark blemishes that appeared and disappeared across its surface. By 1859, he'd accumulated thousands of drawings meticulously dated and annotated. He was building a record trying to understand the rhythm of these mysterious spots. Were they clouds, holes, mountains? No one knew. But Carrington was determined to find a pattern. That Thursday morning, just before noon, he was tracking a particularly large group of sunspots near the center of the sun's disk, when 2 brilliant white patches suddenly appeared within the dark spots. They blazed with an intensity he'd never seen before, bright enough to be visible against the sun's own glare. Carrington stared, stunned. He ran from the room to find anyone to witness what he was seeing. He found one person brought them back, but by the time they returned less than 5 minutes later, the lights had already faded. The entire event lasted no more than 5 minutes. Carrington sketched what he'd seen, noted the exact time, and wrote in his journal that he had observed 2 patches of intensely bright and white light that appeared to be in motion. He had no explanation for them, neither did anyone else, but the sun wasn't finished. What Carrington had witnessed was the visible signature of an X-class solar flare, one of the most powerful ever recorded. The radiation from that flare reached Earth in 8 minutes, flooding the daylight side of the planet with X-rays and extreme ultraviolet light. The ionosphere lit up like a neon sign. Radio hadn't been invented yet, so no one noticed the sudden ionospheric disturbance. But the flare was only the opening act. Behind it, slower and far heavier, a massive coronal mass ejection was already racing toward Earth. Scientists today estimate that the CME was traveling at over 4 million miles per hour, fast enough to cross the 93 million miles between the Sun and Earth in just 17.6 hours. That's unprecedented. Most CMEs take 2 to 4 days to arrive. This one made the journey in less than a day. It hit Earth on the night of September 1st, just after 10 p.m. And when it did, the sky exploded with color. Auroras appeared everywhere, not just in the Arctic, not just in the northern latitudes, but across the entire planet. People in Havana, Cuba saw them. People in the Bahamas saw them. Ships near the equator reported crimson and green lights dancing across the horizon. In the Rocky Mountains, gold miners woke up in the middle of the night, convinced it was dawn. They got out of bed, made breakfast, and started preparing for the day's work before realizing the sun hadn't actually risen. The auroras were so bright that people in the northeastern United States could read newspapers by their light alone at midnight without candles or lamps. Some thought the world was ending. Others thought it was a gift from God. A few thought a distant city was on fire and rushed to help, only to realize the flames were in the sky. But the most dramatic effects occurred in the telegraph systems, the cutting-edge communication technology of the era. Telegraph lines stretched across continents connecting cities and countries through networks of copper wire. On the night of September, first those wires became conduits for something they weren't designed to carry, geomagnetically induced currents. The CME's impact on Earth's magnetosphere generated massive fluctuations in the planet's magnetic field, and those fluctuations induced electrical currents in the long metal wires. Suddenly, the telegraph lines were carrying voltages far higher than normal, not from batteries, but from the Earth itself energized by the storm. Operators reported sparks flying from their equipment. In some cases, the sparks were strong enough to shock the operators or set telegraph paper on fire. Several operators disconnected their batteries entirely and found to their astonishment that the system kept working. The storm was providing the power. Messages could still be sent, transmitted purely by the current induced in the wires by the geomagnetic disturbances. One operator in Boston sent a message to Portland, Maine, with no battery connected at all, riding the wave of the storm's electromagnetic energy. It was eerie, it was unprecedented, and it was a warning. The Carrington event wasn't just a single flare or a single CME. Recent analysis suggests it was actually a double-punch scenario. 2 CMEs launched in quick succession, the second one faster than the first, catching up and compressing the first CME into an even denser, more energetic mass. This cannibalistic interaction amplified the storm's strength. When the combined wave hit Earth, it struck with extraordinary force. The geomagnetic disturbances were so intense that compasses spun wildly, unable to find north. The intensity of the storm is estimated to have reached a DEIST index of negative 1,760 nanoteslas, a measure of how disturbed Earth's magnetic field becomes during a storm. For comparison, the Quebec blackout in 1989 occurred during a storm with a DST of about negative 600, the Halloween storms of 2003 around negative 400. The Carrington event was 3 to 4 times stronger than anything we have measured in the modern era, but here's the key. In 1859, the world ran on steam and muscle. Telegraph systems were useful, impressive even, but not essential to survival. There were no power grids, no satellites, no GPS, no computers, no cell phones. The Carrington event caused disruptions, yes, but it didn't collapse civilization. The world adapted. Telegraph operators replaced their burnt equipment and moved on. Within weeks, the incident was mostly forgotten, remembered only by a few scientists who wondered what had caused such strange atmospheric effects. Carrington himself wasn't sure his observation of the white light had anything to do with the auroras that followed. He published his findings cautiously, noting the correlation, but stopping short of claiming causation. It would be decades before scientists began to piece together the connection between solar activity and geomagnetic storms. Now, fast forward to the present. Imagine the Carrington event happening today with the sun erupting in exactly the same way a double CME racing toward Earth at over 4 million miles per hour. The flare would hit first 8 minutes after the eruption. Satellites on the daylight side of Earth would be flooded with X-rays. Some would go into safe mode, others might fail outright. GPS signals would become unreliable, scrambled by the sudden ionization of the upper atmosphere. High-frequency radio communications would black out. Airlines flying polar routes would lose contact with ground control and would have to reroute to lower latitudes where communication might still be possible. 17 hours later, the CME would arrive. The magnetosphere would compress. Geomagnetically induced currents would surge through power lines, reaching levels far beyond what modern transformers are designed to handle. Transformers would overheat. Some would fail. Circuit breakers would trip. Power grids would begin to collapse, not all at once, but in cascading failures, each outage triggering the next. Within hours, entire regions could be dark. And unlike 1989, when Quebec recovered in 9 hours, a Carrington-level event might cause damage severe enough that recovery takes months or years. High-voltage transformers are not mass-produced. They're custom-built, expensive, and take months to manufacture. If hundreds or thousands of them fail simultaneously, there simply aren't enough replacements available. The economic cost would be staggering. A 2008 report by the National Academy of Sciences estimated that a Carrington-level storm today could cause up to $2 trillion in damage in the first year alone, with full economic recovery taking 4 to 10 years. That's not just the cost of replacing equipment. That's the cost of lost productivity of supply chains disrupted of food, spoiled in warehouses without refrigeration of hospitals, running on backup generators until the fuel runs out. Modern civilization is built on electricity, and electricity is vulnerable to rapid changes in magnetic fields. We've engineered ourselves into a corner, becoming more technologically advanced and paradoxically more fragile. The lesson of the Carrington event is simple. It happened once and it will happen again. Not might, will. The sun operates on cycles we're only beginning to understand, and every few centuries it produces a storm, powerful enough to threaten the infrastructure we depend on. We've been lucky. Since the dawn of the electrical age, we haven't been hit by anything close to Carrington levels. But luck, as they say, is not a strategy, and the clock is ticking. So, the question isn't whether another Carrington event will occur. The question is, what happens when it does? What breaks first? How long does it take to recover? And most importantly, are we prepared? Because the sun, as we've seen, doesn't ask permission. It simply erupts, and we deal with the consequences. Picture this. You wake up one morning, reach for your phone, and the screen is black. Not dead, just blank. No signal. You try to turn on the lights. Nothing. The refrigerator has stopped humming. Outside, the streetlights are dark traffic signals frozen, and the distant hum of the city has gone silent. You check your neighbor's house. Dark. You walk down the street. Everything is dark. The power isn't coming back in an hour. It's not coming back in a day. And slowly, quietly, the realization settles in. This isn't a local outage. This is everywhere. This is what a Carrington-level solar storm could do to the modern world. Not in theory, not in some distant future, right now, today. And the terrifying part. It wouldn't require anything unprecedented. The sun has done this before. It will do it again. We're just living in an era where the stakes have never been higher. Let's start with the power grid. The electrical grid that powers modern civilization is a marvel of engineering, a vast interconnected web of generators, transformers, transmission lines, and substations stretching across continents. In North America alone, the grid consists of over 200,000 miles of high-voltage transmission lines. These lines carry electricity from power plants to cities, stepping the voltage up for long-distance transmission and stepping it back down for homes and businesses. At the heart of this system are transformers, massive pieces of equipment that regulate voltage. They're expensive, weighing hundreds of tons each, and they take months to build. Most utilities keep only a handful of spares on hand because they're so costly and under normal conditions so reliable. But during a geomagnetic storm, normal conditions disappear. Here's how the damage happens. When a CME strikes Earth, it compresses the magnetosphere and generates rapid fluctuations in the planet's magnetic field. Those fluctuations induce geomagnetically induced currents in any long conductor, and power lines are very long conductors. These GICs flow into the grid, entering through the grounding points of transformers. Now, transformers are designed to handle alternating current at a specific frequency, usually 50 or 60 hertz. But GICs are quasi-direct current, slow, steady pulses that don't alternate the way normal electricity does. When a GIC enters a transformer, it saturates the magnetic core, causing it to overheat. The transformer begins to hum, vibrate, and generate excess heat. If the current is strong enough, the insulation inside the transformer breaks down. Hot spots form. In extreme cases, the transformer can fail, catastrophically rupturing and leaking oil, sometimes even catching fire. On March 13, 1989, this exact scenario played out in Quebec. A geomagnetic storm struck Earth, inducing currents in the Hydro-Quebec power system. Within 90 seconds, the entire grid collapsed. 6 million people lost power. The outage lasted 9 hours, and while that sounds manageable, it was only because the storm wasn't strong enough to cause permanent damage to the transformers. Engineers were able to restart the system once the storm passed. But if the storm had been stronger, if it had been Carrington level, those transformers might not have survived. And replacing a high-voltage transformer isn't like replacing a light bulb. It can take a year or more to manufacture a new one, and during that time, the grid stays down. Now scale that up to a continent. A Carrington-level storm doesn't hit just one region. It hits everywhere on the daylight and evening side of the planet. Multiple grids would be affected simultaneously. Transformers would fail across North America, Europe, Asia. The spares wouldn't be enough. Manufacturing couldn't keep up. And without electricity, almost everything else stops working. Water treatment plants need power. Hospitals need power. Refrigeration, heating, communication. All of it depends on a functioning grid. Research suggests that if a major urban area were without power for more than a week, the social and economic consequences would be severe. Food supplies would run out. Fuel pumps wouldn't work. Emergency services would be overwhelmed. Within days, the modern world would start to look very different. But the grid isn't the only vulnerability. Satellites are just as fragile, maybe more so. There are over 5,000 active satellites orbiting Earth right now, and they're all exposed to the space environment with no atmosphere to protect them. During a geomagnetic storm, the outer Van Allen belt swells with high-energy particles, and satellites passing through it are bombarded with radiation. Solar panels degrade, electronics glitch. In some cases, the satellite's computer reboots, putting it into safe mode. In the worst cases, the satellite is permanently damaged and becomes space junk. This has already happened. During the March 1989 storm that blacked out Quebec, a communication satellite called Anik-1 experienced a power failure and tumbled out of control. It took months to recover. During a storm in January 1994, two communication satellites, Anik-1 again and Anik-2, both failed. The disruptions affected television, broadcasts, phone services, and data transmission across Canada. And those were relatively moderate storms. A Carrington-level event could disable dozens, possibly hundreds of satellites. GPS would fail. Weather forecasting, which depends on satellite data, would become unreliable. Communication networks would collapse. Military operations that rely on satellite intelligence would be crippled. The modern world doesn't just use satellites for convenience. We depend on them for survival. Then there's GPS, which deserves its own discussion, because it's woven into nearly everything we do. Your phone uses GPS. Your car uses GPS. Ships and airplanes navigate with GPS. Farmers use GPS to guide tractors. Banks use GPS timestamps to synchronize transactions. If GPS fails, it's not just inconvenient, it's catastrophic. And GPS is incredibly vulnerable to solar storms. The system works by measuring the time it takes for signals to travel from satellites to receivers on the ground. But those signals pass through the ionosphere, and during a geomagnetic storm, the ionosphere becomes turbulent, scattering and delaying the signals. The receiver's calculations become inaccurate. Instead of pinpointing your location to within a few meters, it might be off by hundreds of meters, or it might not be able to calculate your position at all. In 2015, a relatively minor solar storm caused GPS errors of up to 10 meters across parts of Europe. That's enough to make navigation apps useless, to throw off automated systems, to cause problems for anything that depends on precise location data. Now imagine a Carrington-level storm. GPS could be unusable for days. Planes would have to rely on older navigation systems. Ships would resort to charts and compasses. Delivery trucks, which use GPS for routing, would face delays. It sounds almost quaint, like stepping back in time. But in a world where efficiency is measured in minutes, where supply chains are optimized to the point of fragility, even small delays cascade into major problems. And then there's the internet. Most people assume the internet is invulnerable, spread across so many cables and servers that no single event could take it down. But the internet, for all its redundancy, still relies on physical infrastructure, undersea cables, data centers, power supplies. A study published in 2021 analyzed the vulnerability of the internet to solar storms and found that long undersea cables which connect continents are particularly at risk. These cables have repeaters, amplifiers, spaced every 50 to 100 kilometers along the cable to boost the signal. Those repeaters are powered and controlled electronically. If a geomagnetic storm induces currents in the cables, it could damage the repeaters, severing the connection. Repairing undersea cables is slow, expensive, and logistically complex. If multiple cables failed, simultaneously entire regions could be cut off from the global internet for weeks or months. There's also the issue of timing. A Carrington-level event today wouldn't just hit infrastructure that didn't exist in 1859. It would hit a world that's far more interconnected, far more dependent on just-in-time logistics and global supply chains. If the power goes out in one country, it doesn't just affect that country. It affects everyone who depends on goods produced there. A blackout in China would disrupt manufacturing worldwide. A blackout in Europe would strain global financial systems. We've built a world of extraordinary efficiency and equally extraordinary fragility. We've optimized for normal conditions, and a geomagnetic storm is anything but normal. So, what would actually happen if the Carrington event struck today? The flare would hit first, flooding the daylight side of Earth with X-rays. Satellites would begin to fail. GPS would degrade. Radio communications would black out. Then, hours later, the CME would arrive. The magnetosphere would compress. Auroras would appear at the equator. And geomagnetically induced currents would begin flowing through power grids, pipelines, railways. Transformers would overheat. Some would fail. Power grids would collapse not all at once, but in waves, as each failure triggered another. Within a day, large portions of North America, Europe, and Asia could be without power. Hospitals would switch to generators. Water systems would fail. Food would spoil. Communication networks would struggle. And all of it from a single eruption on the sun, 93 million miles away. The 2008 National Academy of Sciences report estimated 20 to 40 million people in the United States alone could be without power for months. That's not alarmism. That's based on models of grid vulnerability, transformer availability, and the likely strength of a Carrington-level storm. And the damage wouldn't be limited to infrastructure. There would be human costs, deaths from lack of medical care, from exposure from accidents and the chaos. Economic costs trillions of dollars in lost productivity, in damaged equipment, in delayed recovery. Social costs. The breakdown of systems we take for granted, the loss of normalcy. The realization that we are not as insulated from the cosmos as we thought. But here's the strange part. We know all of this. Scientists have been warning about the threat of solar storms for decades. We have the data. We have the models. We know what needs to be done to protect the grid better, forecasting improved shielding plans for rapid recovery. And yet, progress has been slow. Why? Because the threat feels distant. Because the last Carrington-level event was over 160 years ago, before most of our infrastructure existed. Because it's easy to ignore a danger you can't see even when you know it's coming. But the sun doesn't care about our complacency. It will erupt when it's ready. And when it does, the only question will be, did we prepare or did we wait too long? The answer might determine whether we lose power for days or for years. But before we talk about what we can do to prepare, we need to understand how we even know these storms are coming. How do we watch the sun? How do we measure its violence, and how much warning do we really have? Right now, as you listen to this, there's a satellite floating between the Earth and the sun, about 1 million miles away, watching. It's called the Deep Space Climate Observatory, or DSCOVR, and it sits at a point in space called Lagrange Point 1, a gravitational balance point, where the pull of the Earth and the sun cancel out, allowing the satellite to hover in place, perpetually staring at the sun. It's our early warning system, our lookout, our canary in the coal mine. And when a coronal mass ejection erupts from the sun and heads toward Earth, DSCOVR is the first to know. It measures the speed, the density, the magnetic orientation of the incoming plasma, and then it sends a message back to Earth if the storm is coming. You have about 15 to 60 minutes. That's it. That's all the warning we get. 15 to 60 minutes. Think about that. 60 minutes to alert power grid operators, to put satellites into safe mode, to reroute airline flights, to warn astronauts aboard the International Space Station. 60 minutes before the plasma slams into Earth's magnetosphere and the geomagnetic storm begins. It's not much time. It's barely enough time. And yet it's infinitely better than what we had before. Because for most of human history, we had no warning at all. We didn't even know solar storms existed. We just saw the auroras, felt the effects, and wondered why the sky was on fire. The era of space weather forecasting began in the 1970s with the launch of satellites capable of observing the sun in wavelengths invisible to the human eye. Before that, scientists were essentially flying blind, watching sunspots through telescopes and hoping to infer what the sun might do next. But sunspots are just symptoms. They don't tell you when an eruption will happen, or how strong it will be, or whether it's aimed at Earth. It's like trying to predict earthquakes by looking at fault lines. You know where the danger is, but you don't know when it will strike. Satellites changed that. For the first time, we could see the corona, the magnetic field, the flares, as they erupted, the CMEs as they launched. We could measure the sun's violence in real time. One of the most important tools we have is the Solar Dynamics Observatory, or SDO, launched by NASA in 2010. SDO orbits Earth in a geosynchronous orbit, giving it a continuous, uninterrupted view of the sun. It takes an image of the sun every 0.75 seconds. That's over 100,000 images per day in 10 different wavelengths of light, from extreme ultraviolet to visible. The images are stunning, revealing details of the sun's surface and atmosphere that were invisible just a few decades ago. You can watch plasma flowing along magnetic field lines, see flares erupt in real time, observe sunspots forming and dissolving. It's like having a high-definition live stream of the sun, updated continuously. But SDO doesn't just produce pretty pictures, it provides data. Scientists use those images to track active regions, to monitor the buildup of magnetic energy, to identify areas where eruptions are likely. Then there's SOHO, the Solar and Heliospheric Observatory. A joint mission between NASA and the European Space Agency launched in 1995 and still operational nearly 3 decades later. SOHO sits at the same Lagrange point 1 as DS-SCOVAR, but it's equipped with a different set of instruments, including a coronagraph, a device that blocks out the sun's bright disk to reveal the fainter corona around it. This is crucial for detecting CMEs. When a CME erupts, it lifts off the sun and expands outward, and a coronagraph can see that expanding cloud of plasma as it moves through the corona. If the CME is headed toward Earth, it appears as a bright halo around the sun because we're looking at it head-on. That's when the alerts go out. That's when forecasters start calculating how fast is it moving, how dense is it, when will it arrive. But here's the problem. SOHO and SDO can tell us a CME has been launched, but they can't tell us everything we need to know. They can estimate the speed and the mass, but they can't measure the most important factor, the magnetic orientation. Remember, when a CME hits Earth, the damage it causes depends on how its magnetic field interacts with Earth's magnetic field. If the CME's field is aligned with Earth's both pointing north, for example, the impact is relatively mild. The fields reinforce each other, but they don't reconnect. If the CME's field is pointing south opposite to Earth's, that's when reconnection happens. That's when the magnetosphere cracks open, particles pour in, and the geomagnetic storm intensifies. And we can't measure the CME's magnetic orientation until it reaches DS-SCOVAR about 1 million miles away from Earth. By then, the CME is less than an hour from striking Earth. That's our warning window. Scientists have tried to improve the forecasting models to predict the magnetic orientation earlier, but it's difficult. The magnetic field inside a CME is complex, twisted, constantly evolving. As the plasma travels through space, sometimes the field flips orientation mid-flight. Sometimes 2 CMEs merge, and the magnetic structure becomes chaotic. It's like trying to predict the shape of a cloud before it forms. You can make educated guesses, but you won't know for sure until you see it. And by the time you see it, it's almost too late. Still, we've gotten better. The NOAA Space Weather Prediction Center in Boulder, Colorado, operates 24 hours a day, 7 days a week, monitoring the sun and issuing forecasts. They use data from dozens of satellites, ground-based observatories, and computer models to predict when solar storms will hit and how strong they'll be. It's not perfect. The models sometimes overpredict, issuing warnings for storms that turn out to be weak. Sometimes they underpredict missing storms that end up stronger than expected. But on average, the forecasts are reliable enough that industries have begun to take them seriously. Power companies monitor space weather and take precautions when a storm is predicted. Airlines reroute flights over the poles to avoid radiation exposure. Satellite operators put their spacecraft into safe mode, turning off non-essential systems to reduce the risk of damage. One of the more interesting developments in space weather forecasting is the use of ensemble modeling, the same technique used in weather forecasting on Earth. Instead of running a single model and hoping it's accurate, scientists run dozens or even hundreds of models each with slightly different initial conditions, and then look at the range of possible outcomes. If all the models agree that a storm will hit, confidence is high. If the models diverge, showing some scenarios with strong impacts and others with weak impacts, the forecast becomes less certain. It's an acknowledgement of the inherent unpredictability of space weather. The sun is chaotic. Plasma dynamics are nonlinear. Small changes in initial conditions can lead to vastly different outcomes. But by running multiple models, forecasters can at least quantify the uncertainty and provide probabilistic forecasts. There's a 60% chance of a moderate geomagnetic storm, a 20% chance of a strong storm, and a 10% chance of a severe storm. But even with all these tools, we're still fundamentally reactive. We watch the sun, we see the eruption, and then we wait to see if it's coming toward us. We can't stop it. We can't deflect it. All we can do is brace for impact. And that's frustrating because the consequences of a major storm are so severe. Imagine if hurricane forecasting worked the same way if meteorologists could only tell you a hurricane was coming an hour before it made landfall. You wouldn't have time to evacuate. You'd barely have time to board up the windows. That's essentially where we are with space weather. We've made enormous progress, but we're still operating with a very short warning time. There have been proposals to improve the situation. One idea is to place additional satellites around the sun, positioned to give us a side view of CMEs as they erupt. Right now, we only have a view from the Earth-Sun line, which makes it hard to tell if a CME is aimed at us or off to the side. A satellite positioned 90 degrees away from Earth would be able to see the CME's trajectory more clearly, giving us earlier and more accurate warnings. NASA has launched missions in the past, like Stereo, which placed 2 satellites in orbits ahead of and behind Earth to provide this kind of stereoscopic view. But the Stereo satellites are no longer in optimal positions, and there's currently no replacement mission planned. It's a gap in our observational network, and it leaves us more vulnerable than we need to be. Another challenge is the sheer volume of data. Satellites like SDO produce terabytes of data every day, far more than any human can analyze manually. So, scientists have turned to machine learning training algorithms to identify active regions, to classify flares, to predict eruptions. These AI models are getting better, sometimes outperforming human forecasters in terms of speed and accuracy. But they're not perfect. They can't replace human judgment, especially in ambiguous cases where the data is unclear. The future of space weather forecasting will likely be a hybrid approach, AI handling the routine monitoring and pattern recognition, with human experts stepping in for critical decisions. And then there's the communication challenge. Even if we have perfect forecasts, they're useless if the information doesn't reach the people who need it. Power grid operators, satellite operators, airline pilots, emergency managers, all of these groups need timely, accurate, and actionable information. NOAA has made progress in this area, developing alert systems and working with industries to integrate space weather forecasts into their operations. But it's still a work in progress. Not every utility monitors space weather. Not every airline has protocols for solar storms. There's a gap between the science and the implementation, and closing that gap could be the difference between a manageable disruption and a disaster. So, where does that leave us? We have the tools to see the sun, to measure its violence, to predict with some uncertainty when storms will arrive. We have about 15 to 60 minutes of warning before a CME hits, and a few hours to a day if we're lucky and the storm is slow. That's better than nothing, but it's not enough to prevent damage. It's enough to mitigate some of the worst effects, to shut down vulnerable systems, to take precautions. But it's not enough to stop the storm from hitting. And that's the fundamental reality we have to accept. We live under a star that erupts, and we've built a civilization that's vulnerable to those eruptions. We can watch, we can measure, we can prepare, but we can't escape. The sun is always there, always churning, always capable of unleashing another Carrington event. And when it does, the only question will be, did we see it coming? Did we listen to the warnings? Or did we, as humans so often do, assume it wouldn't happen to us? Because the sun doesn't care about assumptions. It only cares about physics. And the physics says another storm is coming. It's not a matter of if, it's a matter of when. But knowing the storm is coming is one thing. Living through it, understanding what it means for us, for our fragile connection to the cosmos, that's something else entirely. So, here we are at the end of this quiet journey through fire and magnetism, through storms we can't see and dangers we rarely think about. We've watched the sun tear itself apart, watched plasma race across 93 million miles of emptiness, watched Earth's invisible shield bend but not break. We've walked through history, through Carrington's observatory, through the blackout in Quebec, through the near miss of 2012, when the universe's timing saved us by 9 days. And now, as the story winds down, as your breathing slows and the world outside grows quieter, There's really only one question left. What does it all mean? What do we do with the knowledge that our star, the same star that gives us every sunrise and every harvest, can also reach out and touch us with violence? The truth is, we live in the shadow of a star that doesn't always love us back. It gives yes. It warms the oceans, drives the weather powers. Photosynthesis makes life itself possible. But it also takes. It erupts. It flings pieces of itself into the void, and sometimes those pieces find us. We orbit a furnace, a ball of plasma held together by gravity and governed by forces we're only beginning to understand. And for all our technology, for all our satellites and forecasts and models, we're still fundamentally at its mercy. We can watch, we can measure, we can prepare to some degree, but we can't control the sun. We can't ask it politely to calm down. It will do what stars do, burn, churn, and occasionally explode. And we have to live with that. But here's the strange beauty in that vulnerability. We've been living under this restless star for all of human history, through every civilization, every empire, every moment of joy and suffering. The same sun that shone on the pyramids on the Roman Forum, on Carrington's observatory, shines on us now. It's been erupting for billions of years long before we were here to notice. And yet, life persists. We persist. Not because we're invulnerable, but because we're adaptable. We learn. We build shields, some physical, like the magnetosphere, some conceptual, like the forecasting systems we've developed. We study the cosmos not to conquer it, but to survive it, to understand our place within it. Think about the progress we've made. A century and a half ago, Carrington saw a flash of light and had no idea what it meant. Telegraph operators were shocked by sparks and couldn't explain why. The Carrington event happened, the sky turned red, and the world moved on, mostly unaware of how close it had come to something catastrophic. But we know better now. We've sent satellites to watch the sun. We've mapped its magnetic field, measured its eruptions, cataloged its cycles. We've built models that can predict with reasonable accuracy when a storm will hit and how strong it might be. We've learned to read the sun's moods, to see the warning signs, to take precautions when necessary. That's progress. That's humanity doing what it does best, taking a threat we don't fully understand and slowly, patiently figuring it out. And yet, progress doesn't mean safety. We're more aware of the danger now, but we're also more vulnerable. We've built a world that runs on electricity, that depends on satellites, that assumes the power will always be there when we flip the switch. We've optimized for efficiency, for speed, for convenience. And in doing so, we've made ourselves fragile. A Carrington event in 1859 was an inconvenience. A Carrington event today could be a catastrophe. That's the price of modernity. We've gained so much communication, transportation, access to information, but we've also created new points of failure. The sun hasn't changed. We have. So, what do? Do we retreat, strip away the technology, go back to a simpler time when solar storms couldn't hurt us? Of course not. That's not realistic and it's not desirable. The answer isn't to live in fear of the sun. The answer is to respect it, to acknowledge that we're part of a larger system, a solar system, where the sun is the dominant player and we're just passengers on a small planet trying to make the best of things. The answer is to invest in resilience, to harden the power grid, to build redundancy into critical systems, to improve forecasting. So we have more than 15 minutes of warning, to take the threat seriously, not as a distant abstraction, but as a real measurable risk that could happen at any time, because the sun is already waking up. We're climbing toward the next solar maximum, expected around 2025 or 2026. Sunspots are increasing, flares are becoming more frequent. CMEs are launching with greater regularity. The sun is entering its active phase, and with it comes an elevated risk. Not a certainty most solar cycles pass without major incident, but a heightened probability. And every eruption, every storm is a reminder that the danger is real. We've been lucky so far. The big one hasn't hit us yet. But luck, as we've said, is not a strategy. Luck runs out. Have you ever thought about how strange it is that we can predict hurricanes days in advance, but we can only predict space weather hours in advance, that we can model climate change decades into the future, but we can't tell you with certainty whether a CME will hit Earth until it's almost here? It's humbling. The universe is vast, and our understanding of it is still incomplete. We've learned so much, but there's so much more we don't know. And maybe that's okay. Maybe the point isn't to have perfect knowledge, perfect control. Maybe the point is to keep watching, keep learning, keep adapting, to live with uncertainty, not because we have to, but because that's the nature of existence. We're small, the cosmos is large, and sometimes the best we can do is pay attention and hope we're ready when the storm arrives. The auroras will come again. They always do. Green and red curtains of light dancing across the polar skies, born from the collision of particles and atmosphere, beautiful and violent in equal measure. People will look up and marvel, take photographs, feel something ancient and primal stirring in their chests. And most of them won't realize they're watching the aftermath of an explosion, the tail end of a journey that began 93 million miles away in the heart of a star that doesn't care whether we notice. The auroras are a gift and a warning. They say you're alive because the shield held, but the shield won't hold forever. So, what have we learned tonight? That the sun is not a constant, that the space between us is not empty, that the technology we depend on is fragile, that we live on a planet protected by an invisible field generated deep in the Earth's core, and without it, we'd be as dead as Mars. That Richard Carrington sketching sunspots in 1859 witnessed something humanity wouldn't fully understand for another century. That the storms will come again, and when they do, the only question is whether we'll be ready. But more than any of that, we've learned that we're part of something bigger. We're not separate from the cosmos, insulated by atmosphere and magnetism. We're in it orbiting a star subject to its whims dependent on its light. And that's not a weakness. It's a connection. The sun made us. Its light fed the plants that fed the animals that evolved into us. The carbon in our bones, the oxygen in our lungs, the iron in our blood, all of it was forged in stars long ago before the sun even existed. We're made of star stuff, as Carl Sagan said, and we orbit a star, and sometimes that star reminds us of the relationship. Sometimes it reaches out and touches us not with warmth, but with fire. And maybe that's the real lesson, that we're part of a dance we didn't choose, a cosmic rhythm set in motion billions of years ago. The sun will rise again, as it always does. It will warm the earth as it always has, and sometimes unpredictably it will erupt, and we'll have to deal with the consequences. That's the contract. That's the price of living on a planet in orbit around a star. And as long as we remember that, as long as we respect the sun's power, as long as we prepare for the storms instead of pretending they won't come, we'll be okay. Not invulnerable, but resilient. Not fearless, but aware. The sun will wake again. It always does. And we will watch hoping it wakes gently, but ready if it doesn't. Because the fire is always there burning just beneath the light. And we live every single day in its glow and its shadow. Thank you for drifting with me through this story, through the science and the silence, through the danger we can't see but can't ignore. If you've made it this far, if these quiet journeys into the cosmos bring you comfort or curiosity, I hope you'll stay a while longer. There are more stories waiting, more stars, more mysteries, more wonders hidden in the dark. Until then, sleep well. Dream gently. And when the sun rises, remember, it's not just light. It's a reminder that we're alive under a star that gives everything and asks for nothing except perhaps that we pay attention. Good night,